Hey everyone, I'm Steven. I work at Samsara, as mentioned. At Samsara, we've been using GraphQL for about almost 2 years now in production. And so today I want to talk a little bit about how we use its type system specifically in our system. So first, a little bit about Samsara. We are a hardware and software sensor company, and so that means we build physical hardware devices, then we build some software on top of that for some interesting use cases. One example of this is we have a fleet tracking product, and so in this specific example, we have our vehicle gateways. They connect into like the debug port on the car, essentially, or car trucks your fleet. And then we're able to take telemetry data out of that, send it to our backend systems, and then and then add some, build some software on top of that. So here we have an example of a view where we can see a truck and how its engine is doing, the engine speed, if it's connected or not, things like that. So if we peek a little bit about what's going on behind the scenes, it looks sort of like this. We have our gateway device that runs Go programs. It sends its data over to our backend service for processing. That's also written in Go. And then all of this is abstracted away behind our GraphQL layer, which we call Thunder. And so Thunder is a Go-based GraphQL service, and that's the gateway for sort of all of our front-end applications to be interacting with any of our backend. And so in this example, we have our web application and our React Native mobile application. They're both using React and TypeScript. And so GraphQL is sort of at this last level here. If we look at an example of sort of like the different types of features that we might have, this is not a screenshot. I took this off of our marketing page. But we have a lot of different use cases, and we can sort of see that we have lots of different types of data flowing through the system. So for example, a vehicle might have a dash cam connected that's constantly taking imagery. It might have a temperature sensor for keeping track of the state of some food that's being shipped. We might be tracking the location or speed of some vehicles or who's driving those vehicles. And so there's a lot of different types of things going on here. And what we've realized is as we build more features, we see more problems with how to have a shared definition for some of these things. And that's where the GraphQL type system comes in. I think we've heard a lot about the schemas in the past few talks. But just to go over it again a little bit, here's an example of what a schema for one of our gateway devices might look like. A device might have a name, an ID number, it might have a current driver, and maybe a set of locations that it's associated with. And so the GraphQL schema definition language lets us specify these things in a declarative way. And so this is the hammer that we end up using for sort of helping us have a shared definition across our system, more static typing. And so if we think about what a type system gets us, it's really two big things. One of them is safety, and the other is editor tooling. And so safety sort of means that at compile time, we get a lot of guarantees about what our program can and can't do. And without actually executing anything, you can sort of understand that a whole entire class of bugs is probably not going to happen. We take advantage of this in a number of ways. One example is when we deploy new versions of our front-end or back-end application, we verify that those applications work with previous versions of the apps as well. So if we accidentally deploy two versions at the same time, or we're transitioning from old versions of the front-end to new versions, we can make sure statically that these things will work correctly. And as a secondary benefit, we get a lot of editor tooling. And so while you're actually developing software, you get nice things like autocomplete, go to definition. The type system can tell you if you've made a mistake spelling something. In particular, I want to talk about how the type system interacts with a lot of different software you might also be using. And so for our example, we use at Samsara both GraphQL and TypeScript together. So I want to take a look at a quick example for how this might be useful. So going back to our really simple device schema, here we have a device, it has a name, and then we have a really simple way of fetching the device by its ID number. So we might write a query like this where we're just fetching that information. If we look at what the JavaScript might look like if we were writing the component for this, let's say we have some component and it's really just showing the name. It's very, very simple. It reads out of the props and it shows the device. And then we connect it to our GraphQL system and maybe pass it the input arguments. So in this case, 202, et cetera. So right off the bat, if you've been observing astutely, you'll notice that I've already made two bugs here. One of them is that I wrote full name instead of name. And then down here for the input arguments, I wrote device ID, but back in my query, I wrote ID instead. So the problem here is that your tools don't actually care about this unless you tell them to. And so here, Webpack is like, well, I compiled it successfully. Feel free to ship this into production. And that's a problem. The tool is not giving us sort of safety in ways that it could automatically know about. And so that's where TypeScript comes in. TypeScript is just a typed variant of JavaScript. Some of you might also use Flow. And so we can use TypeScript to give the program hints about what we should expect the data to look like. And so, for example, the simplest thing we might do is decide to write our ontological types out by hand. And so in this example, I look at my schema and I look at my query, and I decide, OK, I need to like figure out what the result of this looks like. I'll type it all out. And then I'll do the same thing for the input arguments. So at the top here, I have the device and the name, and then below the input arguments. And so what this looks like is I'll change my JavaScript a little bit to start looking like TypeScript. I tell it what the props actually look like. So above, I tell it the change here is that I've now added this little annotation, and the annotation tells the system, here's what the type should be. And then immediately, the TypeScript compiler gets really angry with us. It's like, hey, I don't really know what you're doing here. Full name doesn't actually exist on this query result. And oh, by the way, you're missing the property ID. I was really looking for that here. So this works pretty well. We could write our types for the inputs and outputs by hand. But if you start thinking about it, this is really just the simplest example we could come up with. I only have one struct here, and it's just got a name. And so if we look at what a more complicated GraphQL query might look like, let's say we throw in a bunch more arguments, we have a lot more fields, and just to make things really complicated, we'll add like a couple of fragments. And so this becomes really problematic because now like I have to type a lot of stuff. I have to keep it in sync with my query. I have to like make sure I don't accidentally add additional bugs by like making a typo. And it doesn't even fit on my slide. It's pretty much no good. And so as it turns out, if we go back to our example of what the type definition looks like and what our GraphQL schema looks like, these things look pretty similar. We have all the information we need just looking at the GraphQL schema. And as it turns out, the GraphQL schema and TypeScript types can more or less be mapped one-to-one this way. A lot of people in this, working in this building have realized that we could do this as well. And so they built a tool called apollo-codegen. And what apollo-codegen does is it basically does what we did sort of visually there, where it takes your schema, it takes the GraphQL documents, does a little bit of magic, and then it outputs the types without us actually have to type physically with our hands. So how does this actually work? If we take a look at our schema and our query, we can see that in the query itself, we can already see that the arguments are there for us. So I expect an ID, it must be a number, and it's not optional. And so looking at this, I can just emit a string by traversing the GraphQL AST and understanding sort of what's going on inside of the query arguments. And similarly, if I look at the result of the query, so the device and name, I can match that up against the schema, understand that the device resolver returns the device type, and then the device type has a name on it. And so then I can output the query result type as well. So this is pretty great. We have a codegen tool. We can run it on the command line. We don't need to manually type out any of our types, and we get all the benefits that we talked about earlier. And this sort of looks like the change from our previous example is we import the types from our generated type file, and then we start using them. Great. So now we have type safety in a little bit of our code. If we take a step back and think about the entire data pipeline for where our information might come from, we can draw a little bit of a circle around shared type land. So everything inside the ring, we can now have a single definition for any given piece of data that might flow between them. So can we go further? There's a lot more stuff that's not inside shared type land yet. What can we do about that? Well, if we think about sort of what's actually happening on the GraphQL server itself, we also need to be writing the server implementation of how do we actually go fetch this device from the database, what fields does it have, like what else can you query off of it. And so this is a little bit of the Go code that you might write inside of our Thunder implementation. And if you squint a little bit, you'll notice that this looks pretty similar to our GraphQL schema as well. it turns out that both systems have a sort of static typings, and we can actually just map the Go types to the GraphQL schema as well. And so we use this through a process called reflection. And reflection in some languages is essentially a way for a program to ask questions about itself during runtime. And so at the initialization of the GraphQL server, when we register that, like, hey, we have a device resolver and it has some fields, and then we also have the device itself, we can introspect on what those fields actually are and what those types are to generate our GraphQL schema automatically. And so here, we might look at the device arg struct and say, OK, great. The input argument is just an ID, and it's an int64. I can look at that and look at the output and say, OK, great. There's a resolver here, and it'll return you a device. And similarly, we can look at what's actually on the device type itself and generate a GraphQL schema for that as well. Great. So now we have another tool. We can take our our Go types and generate the GraphQL schema out of that. And so if we look at shared typeland again, we can expand our borders a little bit, and now we've also encapsulated the GraphQL service. And so anything that you might express inside of the Go code, you can also express inside of the TypeScript environment as well. And so the last question we might ask is, can we go even further? So there's like these two stragglers here that we haven't quite gotten into our shared typeland yet. And that's the gateway hardware device itself, and maybe some of our data processing backend services. So if we take a look at what's actually going on behind the scenes, it turns out that we don't use GraphQL between these things, and it kind of doesn't make sense to. Between the gateway device and the backend services, we're not sort of like, we don't have a lot of different components that are trying to fetch various disparate types of data. It's really just we want to pass in messages between the different services, and we want them to be like reasonably typed. And so GraphQL isn't quite the shape of a solution that we need here. And so instead we use protobufs. And protobufs are essentially a serialization format for sending data messages. And so you can think of it kind of like Thrift, or maybe a version of JSON that has a better type system. So as it turns out, we have also protobuf types and Go types that can also be mapped together. Using the protobufs compiler, we can take our protobuf types and then compile Go codes right out of it, using the tools called protocg and Go. And so using our example protobuf, let's say that we have this little message for returning data out of a temperature sensor and sending it through our backend service. We can take a look at the time. We can take a look at the fields and say, OK, there's a time here, and there's a value for like what the actual temperature is. And then we can take all of that and compile it down into a Go type that we can use. So there's time and a double value. And so the last tool here that we have now is a way to take our protobufs and generate Go code out of them. And so shared typeland grows a little bit bigger at this point. And so now, sort of taking the fully zoomed out view of this, we can now share types across all parts of our system. And for a piece of code that might interact with multiple parts of the services, you only ever have to write a type definition once, but you get to benefit everywhere. This is pretty great. The schemas and typings can pretty much never be out of sync because we use these automated tools to build them. We still get the benefits of having autocomplete, go to definition, outlines, all of this stuff in our editing environment. So it doesn't matter if you're typing in, or you're writing code in a Go file or a GraphQL file or a TypeScript file. You get the benefits of the system knowing what you're talking about all the time. And it's just kind of pretty cool that we can write a type definition that works on a hardware device, plummet all the way through our backend services, and even use more or less the same, at least origin for that type definition in our front-end service as well, or front-end application rather as well. And the best part of this is it's more or less available to everybody to use. All of the things that we've talked about are open source here. And so Thunder, our GraphQL service, we've had open source for about the last year or so now. Apollo-codegen is also available for open source. And Protobufs have been around since apparently the early 2000s. And so all of the tools are sort of available for folks to use. And so we think that this is a really powerful default for developers. They don't really have to think about like, oh, I need to keep my schemas in sync, and I need to like make sure how to plumb this shared definition through a bunch of different things. Really, it's just you write a type definition once, and you benefit everywhere. The computer does a lot of the heavy lifting for you. We think this is really great, and we hope you, we encourage you to try it as well. Thanks. Any questions? Yes?
What do you do with int64s that are bigger than JavaScript?
Yeah, so now we get to bonus slides. Let's see. Great. So type mapping is not always one-to-one. There are some concepts that like don't quite map between the different type systems. And so one of them, for example, is the number type. For float64s, we basically ignore this problem. And so when int64s come into the system, we cast them into float64s. And when they leave the system, they only have the precision of the float64 as well. This is a little bit problematic, but we haven't really found real issues where, because we're lacking the precision, we've like seen really egregious bugs.
Bumping up packages everywhere?
Mm-hmm. Yeah, so I had a couple slides where I'm running these things manually. We do those as parts of compilation for the different steps of our system. So when you recompile the Go service, for instance, it emits the .graphql or the .json schema file, and then that gets consumed by the TypeScript code. And then at compile time, or sorry, at deployment time, we check all of that as well.
So you deploy your hardware company?
Oh, I see, yeah. So we typically will try to avoid deploying changes that are breaking in that way. And so we can't, like, we won't deploy a hardware firmware change and like the TypeScript change at the same time. Usually the hardware change will go first, and then later we'll add it to our Go system and then our TypeScript system. And so there's a little bit of a manual process there that we would like to see be more automatic, but it's worked pretty well as it is, since you at least get to check that things are safe at every step.
Yeah, let's thank Stephen.